last time we were taking a look at principal component analysis. Okay. So like I was indicating, PCA is a very popular technique in machine learning, classical AI, and even though as we, go into modern AI, which is basically deep learning, what you will see, the general theme is we take a look at classical techniques and make our networks learn those techniques from the data in an automated way. But in my opinion, you can't really understand it very nicely until you know what exactly the technique is that for example, the deep network is trying to learn. So after the break, we'll start to take a look at more deep learning approaches to computer vision. But before we get there, we have to understand some of the very, very important mathematical foundations of representing data, reducing the dimensionality of data, finding out what is important inside the data, right? And this is where the PCA technique comes into play. So as we discussed in the last lecture, the goal of PCA is to reduce dimensionality. Okay, so that only those dimensions which are important are preserved, and further, a secondary goal is as we reduce the dimensionality so that maximum distinction can be made between data. Okay, so as we discussed last time, okay, suppose in 2 dimensions some data is given to us, right? Okay, for example, let's take a look at these 2 data points over here. Okay, or maybe let me make it. Okay, let me make it somewhere here. Okay, suppose these 2 are the data points. Let me redraw. Suppose these 2 are the data points, right? Okay. For example, if we take a look at in the x dimension, there's a little bit of a difference between the 2. Or actually, let me exaggerate a little bit. Okay, let me exaggerate such that, let's say, here's the second data. Anyway, if you take a look at the y dimensions, very less difference. In the x dimension, there is more difference, right? But if we change our x-axis to, let's say, become like this, then you can see we have the maximum distinction between the 2 data. So principal component analysis essentially will reorient the axis so that we can distinguish the data as much as we can. Okay, so how does it do it? Okay, as we went through the last lecture, let me quickly refresh your memory. And then your next assignment will be based on the PCA and the face recognition. Okay, so let's say we have so let me give you an example of the face recognition. It's easy to see. So suppose we have a 100 by 100 image of an incoming face, okay? And let's pretend in our database we have 200 of these images, 100 by 100. So we have 200 different people, okay? So the total is 200 persons. Okay, first thing we do, so remember if we convert each row, pretend it's already been converted to grayscale. So if we start putting the first pixel over here, second pixel over here. So start assembling it into one vector, right? So 100 by 100 will change. Once we assemble it into one column vector, will become 10,000 by 1, right? Okay, so then we can think of each one of these faces or each one of these images like one single point in a 10,000 dimensional space. So pretend in the 10,000 dimensional space, each one of these 200 is just a single point. Okay, so the first thing we do is, because let's pretend all these pictures were taken in high brightness conditions. Okay, so then what will happen is this data will be like shifted, a little bit higher in the X or the Y axis. So a standard technique in analyzing, data, regardless it's vision data or not, is to center it around the 0. Okay, so that we shift this data. So it's still the same, the relative relationship is still the same, but it's all centered around the origin. Okay, so what's the easy way to do that? Easy way to do that is find the mean image. Okay, suppose we call this I bar. So I bar will be basically this pixel plus the same pixel in the second image, same pixel in the third, same pixel in the 200th image, right? Add them, divide by 200. Okay. So then what we can do is we can do, suppose we call this I0 is basically, so let me put it like an approximation over here, I0 minus I bar. Okay. So same way, if we assemble all the 200 images after we have subtracted them from the mean, okay, then suppose those, we call this the I matrix. So as you can see here, so this is basically mean adjusted image. So the first column is mean adjusted I0. Okay, second column will be the mean adjusted I1, right? And so on. Okay, so what will be the size of it? If we have each is 100 by 100, there are 200 of these. So this will be
10,000 by 200.
By 200, right? Okay, so the second step, as if you recall, was find the relationship of each image to another image in our data set. So we do that by computing the covariance matrix. So the covariance matrix could be computed either as I times I transpose or I transpose times I. Whichever gives us lower size, we use that because computationally that's a lot better. Okay. So for example, if we did in this particular example, which one will be better?
Second one.
Second one, right? So if we pick this, then this will be 200 by 200. Okay. And then the next step is compute eigenvalues of covariance matrix. Okay, so if it's a 200 by 200 matrix, as we discussed, we'll get 200 eigenvalues. Okay, corresponding to that, we'll compute eigenvectors. But because our goal is to reduce the dimensionality, okay, suppose we wanted to reduce it to only 30 dimensions, then keep top 30 eigenvalues by magnitude. Meaning it doesn't matter whether it's positive or negative eigenvalue, we are interested in the magnitude, right? Okay, corresponding to these 30 eigenvalues, whatever top, it could be 50, doesn't have to be 30, right? I'm just picking an example so that we can easily see what are the steps of the algorithm. Okay, so corresponding to top 30 eigenvalues, compute eigenvectors. So how many eigenvectors will we get in this case?
Still 10,000 by
No, only 30, right? 30 eigenvectors. Suppose, what will be the size of each eigenvector?
10,000 by 1.
Why 10,000? Where did we get it from?
Sorry?
We got it from covariance matrix,
200 by 200.
which is only 200 by 200. See, if I gave you a 10 by 10 matrix, how many eigenvalues will there be? 10, right? What will be the size of each eigenvector?
10 by 1.
10 by 1. So if it is 200 by 200 to begin with, because that's where we computed the eigenvalues, right? So as you can see, then each eigenvector will be 200 by 1,
Yep.
right? Now let's assemble all the eigenvectors into an EV matrix. So here's the first eigenvector, which as we discussed is 200 by 1. Here's the second eigenvector. Okay, then what will be the size of this if we have 30 of those?
200 by 30.
200 by 30. Okay, so up to this point, you know, as I was saying, also try to see intuitively why are we doing this. Okay, the reason we are doing it is, first of all, covariance matrix will tell us how close each image is to another one. If they are completely similar, covariance produces a high number. If they are dissimilar, it produces a low number, right? So essentially, this is giving us the information how the data is related to each other. Okay. Then the eigenvalues, like I was saying, why are we computing eigenvalues and eigenvectors? Okay, because if we have some data, for example, in two-dimensional space, okay, then remember, eigenvectors are basic. A vector has a magnitude and a direction. One vector could be this way, another vector could be this way, another vector could be this way. Okay, suppose these are unit eigenvectors, meaning their magnitude is 1. Then the eigenvector will give us the direction information. Okay, so it has been proven that if we compute the eigenvalues of the data, then if we take a look at the eigenvector corresponding to the highest eigenvalue, it will always point it in the direction which separates the data the most. For example, you know, it will, as you can see in this direction, there's a high distinction between the data. So that's why we are computing the eigenvalues and the eigenvectors of the covariance matrix, so that we can see how can we distinguish the data most from one another. Okay. Anyway, up to this point, it intuitively makes sense. Okay. So now there's a second part to it, which has a separate purpose. Okay. So let me keep this part separate, second part separate, because after we are done with it, I'll introduce another algorithm where you'll be easily able to understand it. Okay, why are we doing and how that algorithm makes it even better. Okay, so the second part is, okay, so now we basically, so the second part of PCN. Okay, so once eigenvectors have been determined, okay, we want to reduce dimensionality of data. Because in the beginning, in our example, our data was 10,000 dimensional space, correct? In the beginning. Okay, we want to reduce it to 30 dimensions as an example. Okay, it doesn't have to be 30, once again, could be 40, could be 100, could be 80, it doesn't matter. Okay, so the second part of the PCA will basically reduce the dimensionality. Okay. For us to be able to reduce the dimensionality, there's one concept that you should know in general, which is the concept of orthogonality. Okay, so in math, there's a concept called orthogonal functions. Okay, if we have a set of orthogonal functions, so if we have a set of orthogonal functions, then any function can be represented as a linear combination of the orthogonal basis. Okay, so let me first, without being specific, let's pretend somebody gave you set of functions which are orthogonal to each other. Okay, what's the definition of orthogonality in pure math? Let's say if you integrate f1x, f2y. Okay, so if the integral produces the answer 0, for example, x equal to not equal to y. But if x is equal to y, it produces an answer 1. Okay, that means these two functions are orthogonal. Okay, so as an example, okay, maybe x and y was not a good choice over here. As an example, if we have cosine, let's say nx sine mx dx minus infinity to infinity, what you will see is this produces an answer of 1 if m is equal to n. It produces an answer of 0 if m is not equal to n. Okay, so cosine x, sine x are our orthogonal bases over here. Okay, that means any function, so you have some f of x, could be represented as 0.2 cosine x plus 0.3, let's say cosine 2x plus, 0.11 sine 5x, and so on. So it doesn't matter how complicated this function is. Okay, let me see. Okay, suppose a triangular wave, it could be represented as an infinite sum of these orthogonal bases, right? Okay, very similarly, so cosine and sine are not the only orthogonal function. There are hundreds of orthogonal functions in math, right? Okay, some of you would remember sine x over x, which is called sinh of x. If we plot it, it looks like this. Okay, so these also, with if I shift it by m, shifted by n, they also form an orthogonal basis. Okay, for example, there's also called Chebyshev polynomials, also make a set of orthogonal functions, right? Okay, so now let's try to relate it to our problem. Our problem is not a function. Our problem is an image. Okay, so the question is, given an image, so here's some image, can this be represented as some linear combination? So this is what we are trying to do. Linear combination, for example, some coefficient, 0.15 times base image 0 plus 0.27 times base image 1 plus minus whatever 12 times base image n. Okay, so for example, if this is a picture of Bill could be represented by multiplying by some coefficient if we have these base images, right? And for this to work, the mathematical condition has to be satisfied is that these base image 0, base image 1, base image n have to be orthogonal to each other, okay? So these have to be, so base images have to be orthogonal to each other. That's a requirement. Otherwise, this theory doesn't work, meaning being able to represent any image as a linear combination of the base images. Okay, so next question. Okay, see over here, we can easily go through the integral and prove that if m is equal to n, it will produce 1. M and n, by the way, are integers. Okay, and if m is not equal to n, it will produce a 0. So we can go through the math and easily prove. And if this comes out to be this case, then that means cosine nx, sine mx are orthogonal to each other, right? But now the question is, in terms of images, what do we call two images to be orthogonal? Okay?
If with one we can generate the other.
No, see, once again, take a look. If the orthogonality is, if there's no, like m and n are different, right? So it produces 0. So there's some like a product, and what does integral do in
Add up all the
Convolution.
images or in discrete numbers? With it's addition, right?
addition.
It's so as far as orthogonality of base images is concerned,
So addition of all the pixel values.
you're close.
I can vector.
But then there's also a product going on. So there's a
I get
multiplication
vectors
and addition
into the
going on.
addition of
I
all
can
the
vector
pixel
those orthogonal, so
We don't even have to if I gave you two images and I said, are they orthogonal to each other? How would you tell me yes or no? Okay, so let me give you the answer. Okay, for example, let's take a look at x-axis and y-axis. Okay, if I gave you a point over here, whose coordinate is, let's say, x of 1, y of 0. If I give you another point over here, x of 0, y of 1. Okay, if I drew a vector over here, orthogonal means perpendicular, right? Are these two vectors perpendicular to each other?
Yeah.
Yeah, they are 90-degree angle, right? If I now represent it as not like a 1-0 coordinate, but like as a vector. So this is my first point. And my second point is 0, 1.
So the dot product should be 0.
Exactly. So if we take the dot product, which will be 1 times 0 plus 0 times 1 is 0. So if the dot product produces a 0, that means they are orthogonal to each other. Okay. So now let's go to images. These are two-dimensional data.
So the pixel value dot of the both.
But as I mentioned, if I had a 100 by 100 image, could you represent it as a vector? 10,000 by 1.
Yeah. To 10,000 by 1.
10,000 by 1, exactly.
Yeah.
So if I say these two are orthogonal, what does that mean?
So those 10,000 by 1 dot 10,000 by 1 is equal to 0.
If we get it 0, those two vectors are orthogonal to each other. So if somehow we can come up with, let's say, 30 vectors over here as an example, which are mutually orthogonal to each other, meaning inner product of this with this produces a 0. Inner product of this with any other produces a 0. Only with itself it will produce an answer of 1, but everybody else it will produce 0, right? So then we have an orthogonal basis. And according to proven mathematical theory, if you have an orthogonal basis, now you can create any function, or in our case, we can create any image out by simply combining these in a linear way, right? So still the next answer is, how do we know, for example, there's a picture of Bill. Okay, let's pretend we somehow we came up with 30 of these orthogonal base images. Then we wanted to reconstruct Bill by combining these. So how do we know what is the coefficient that it should be 0.15 with multiplied by the base image 0, then 0.27. So that's the next question. How do we know the coefficients? So in other words, what I'm trying to say is we have two problems. So let me write it down for you. So this is the second part of the PCA. Okay, so let me put two problems over here. Okay, number one. Determine orthogonal basis. And in our case, these will be base images, which if we convert it to a vector, do the inner product, it will always produce a 0 with somebody else, but with itself it will produce a non-zero answer, right? Then second problem is determine the coefficients that will be needed to reconstruct an image from orthogonal basis. Okay, so once you understand it, like I said, then as I explain the next algorithm, you yourself will say, hey, this was easy. We know exactly how to do it. Okay, but anyway, so how do we do that? Before we start this step, right? We had created the I matrix. So let me put that over here as a reference. Okay, so this is the mean adjusted I0, then mean adjusted I1, correct? Same thing. And so what was the dimension of this? 10,000 by 200. You guys agree? I matrix was right. Then we created the covariance matrix. What was the dimensions of the covariance matrix? 200 by 200. So this was created as I transpose times I. Then next step was we computed the eigenvalues, eigenvectors. Then we, corresponding to the top 30 eigenvalues, we created the eigenvectors, we assembled them. So for example, this is EV0, this is EV1. Okay, each will be 20 by 1, correct? Oh, sorry, 30 by 1. Because we were picking the top 30 eigenvalues, right? So what will be the size of this EV matrix? 200 by 30. Okay. So before I put more detail over here, let me ask you a question. Okay, suppose here's the image of Bill, right? In our example, we said this will be 100 by 100. My question to you guys is, what will be the size of the base images? So that if we multiply by some number and keep adding, it will give us the same pixels as Bill.
100 by
It has to be 100 by 100, right? Which if I convert it to a vector, what does that mean? What will be the size of this vector? 10,000 by 1. Okay, so as you can see, to answer this question, we need to come up with a set of 10,000 by 1 vectors, right? Okay, so if you easily take a look over here, this is 10,000 by 200, this is 200 by 30. So take a look over here, what will happen if I multiply the I with EV? Suppose I call it EF. And why EF, I will give you the reason in a second. We can call it anything, but for our understanding, EV, because this is eigenvector. I is the original set of images, so this is 10,000 by 30, sorry, by 200. This is 200 by 30. So what will this produce then?
10,000 by 30.
Okay, so this will be 10,000, right, by 1. And how many will there be? 30 columns. So this will be 10,000 by 30. So if you took a look at each column, okay, that will be our base image. Okay, so here's the interesting part, and you will confirm it as you program it and see it yourself. Okay, for us to call one of these columns a base image, what's the requirement?
This product with the other give us 0.
If I took the inner product with any other column, what will it produce?
0.
So then these are orthogonal. Okay, so so if I call the first column, let's say EF0, second column as EF1 and so on. So then if I have any unknown image, could this be represented as 0.13 times EF0 plus 0.28 times EF1 plus whatever minus 0.81 times EF29? Okay, we don't know how we will pick these, but if these were correct, sure, it will reconstruct the image in terms of the basis functions, right? Okay, so coming back to our two problems to solve, do we have the answer to the first problem?
Yeah.
Orthogonal basis is easy. Take the input data, multiply it by the set of eigenvectors, and you'll get the orthogonal basis. And we can, like I said, easily prove it that it's orthogonal basis by taking the inner product of any of these columns and seeing 0.